Mr. Chairman, ladies and gentlemen, my topic today is synthesis of adamantane or zeolite catalyst. Adamantane is a special kind of hydrocarbon compound. Its chemical composition is carbon 10 and hydrogen 16, and it has a diamond-like structure like this. Due to the high symmetry in structure, adamantane is very stable. It is a very useful chemical reagent in organic synthesis and also in pharmaceutical industry. The amino derivative of adamantane is a very effective antiviral agent. It can be used as a preventive drug for influenza and also a drug to combat Parkinson's disease. And at first, adamantane was discovered in crude oil. The separation is very difficult because its content is minute. Then it was produced from multi-step organic reaction process with a very low yield, less than 3%. But catalytic research in the synthesis of adamantane from dicyclopentadiene allows to produce adamantane in much higher yield. Dicyclopentadiene is first hydrogenated on palladium and platinum catalyst to form tetrahydrocyclopentadiene. And then TCD is isomerized on acid catalyst to form ADN. The first catalyst used is the Lewis acid, like aluminum chloride, and the yield is about 10%. Then Mercury used platinum alumina as the isomerization catalyst. The yield was improved, but the catalyst deactivates almost instantly. And then Ola used superacids, used magic acid as the acid catalyst. And the yield was increased a great deal. But the catalyst and reactant ratio is 20:1. And we know this catalyst is very difficult to handle. So this is quite unpractical from the industrial point of view. Recently, Horner reported that this reaction can proceed on zeolite catalyst with in either batch reactor or in fixed bed reactor with a yield of 31%. This is indeed very attractive from the point of view of industry. Acid catalysts are quite complicated. On zeolite catalysts, there are mainly 3 types of reactions. One is the ring opening reaction to form methyl octahydroindium. And then the hydrogenolysis reaction to form carbon 5, carbon 6, carbon 7, and cyclohydrocarbons. And then the isomerization reaction to form ADN. So the aim of my work is to study on the relationships between the activities and selectivities of the reactions and the acidity and pore structure of the zeolite catalyst. These hydrogen H-form zeolites are prepared by ion exchange method. And these are the de-illuminated white zeolites prepared by different methods. The HSY was prepared by secondary synthesis with ammonium fluorosilicate. And HEY was prepared by EDTA extraction. And HUSY by hydrothermal treatment. And these metal cation exchange zeolites were prepared by ion exchange with nitrate solutions. And the reactions were carried out in a 20 milliliter magnetic stirred autoclave. 2 grams of TCD and 1 gram of catalyst were loaded. And it was evacuated first and then filled with hydrogen. Now the results. First, the reactions were accelerated by hydrogen chloride. We can see from the data in this table the total conversion and also the ADN yields were increased after adding hydrogen chloride into the autoclave. In the absence of catalyst in dilute hydrogen chloride atmosphere, no reaction has occurred. In dense hydrogen chloride atmosphere, a small amount of reaction was occurred. From these data, it suggests that maybe the reactions were accelerated or initiated by the additional bronze acidity formed by the dissociative absorption of HCl on zeolites. The influence of reaction temperature and time were studied. As the reaction temperature was raised from 200 degrees centigrade to 250 degrees centigrade, the total conversion and the ADN yield were increased. But above 250 degrees centigrade, less ADN and more MHI were formed. And it was noted that in most cases, the reactions reached steady state around 12 hours. So the following activity tests were run at 250 degrees centigrade for 12 hours in hydrogen plus HCl atmosphere with hydrogen HCl ratio equals 10 to 1. The reactions were carried out on different types of H-form zeolites, and the results were very different. The total conversion, the order of the total conversion is like this. Hn larger than Hy larger than HCSN5. And the ADN yield and the MHI yield are Hy larger than Hn and then larger than HCSN5. For the low hydrocarbons, the yield of the low hydrocarbons is Hn larger than HCSN5 larger than Hy. These are the ammonia TPD profiles of our zeolite catalyst. There are 2 peaks on the profiles. And these are the ammonium TPD data. The second peak corresponds to the strong acidity of the zeolite catalyst, and the peak temperature corresponds to the acid strain of the strong acidity of the zeolite catalyst. And the peak area of the second desorption peak corresponds to the strong acidity of the zeolite. So the acid strain, the order of the acid strain is larger than HCSN5 larger than HY. And the strong acidity is HM larger than HY larger than HCSN5. And we also use N-pentane reactions at low temperatures to characterize the acidity of the zeolite catalyst.
Handling of the non-zeolite catalyst for the selective hydrogenation isolation. Contributed from the President State Classification
I have slides. I have the first slide. I guess, well, first I should say something about my co-author. Wancheng Liu is actually from Beijing. He works at the Petroleum Research Institute in town. He just felt he'd been here too frequently to be a chance for me to come and give the talk. See Beijing. I'm very happy to be here. I think one of the subtexts in American catalysis right now, we saw this in the most recent CNN News, quoting Professor Bell, not yet, please, back to the first slide. I'll say next slide. Is whether those folks working in academia can continue to do catalysis as we have in the past, or whether we can actually contribute to a new way of developing new catalysts with what we can learn on a fundamental level. In other words, is industry going to continue to develop catalysts on the basis of an Edisonian approach, or are they going to learn how to apply the fundamentals that we have uncovered in our research work to design catalysts in different fashions? Next slide, please. And we're going to get back to that question at the end. First, I'm going to talk about some of the work in bimetallic catalysts I've done in my lab in the last 10 years. A brief introduction. I've had some people come up to me during this conference I haven't seen in 10 years and say, what are you up to? So I thought it was a good chance to talk about that. There's basically three ways of looking at bimetallic systems. One way is to look at the bimetallic cluster as a sort of large molecule. I think this is sort of the chemist approach. When you put the large molecule on the surface, it sort of remains a large molecule. And we've had some people discussing that today. I think there's some obvious limitations. The clusters tend to break up and form particles when you get above about 100 degrees C. I saw that in today's work with the ligand supporting the clusters that they carefully kept the temperature down low enough so that they could continue to regard the bimetallic particles or single metallic particles as clusters. A second way is to look at the catalyst, the bimetallic catalyst, as some sort of a perfect surface. And we had some discussion of the perfect surface model of catalysis and limitations earlier today, so I won't go into that. And the third way is I think the material science approach, which we bring to the subject. And in that field, one thinks of metallic substances as undergoing dynamic phase change. They don't stay the same over time. And on the basis of understanding how these transitions, these solid-state transitions take place, under what reaction conditions as a function of temperature, perhaps it's possible to predict the final structure of bimetallic systems and actually use this knowledge to design some catalysts. And of course, I say there are no weaknesses to this technique because otherwise we wouldn't be doing it. Next slide. Actually, all three techniques have their use in presenting an overall understanding of the bimetallic system. When we came into the world of bimetallic particles, there were these 5 similar models of the way bimetallic particle structure looks. Each of them suggests, in essence, that at the metal support interface, there's an oxide that forms, and above that, some sort of an alloy phase forms. There was one slightly different one where someone said there was a special surface alloy in addition to the bulk alloy that would form. And each of these prior studies, there was only a single catalytic chemistry which was ever associated with a bimetallic system. Next slide. We actually felt differently, and the system I'm going to talk about in detail iron rhodium, and my collaborator in that work was Bob Gaddy, who now works at Grace Chemical. But in fact, iron palladium, iron iridium, iron manganese, palladium silver, all those systems we've studied subsequently act in a similar fashion to what I'm going to be talking about for iron rhodium. So this is merely a kind of a sample system. Next slide. And what we found actually is that, and we feel this is consistent with metallurgical understanding of the bimetallic system, is that there are in fact two different reduced states. This one up here, which is a true alloy, and this one down here, which is segregated metals of a bimetallic system. This particular case being iron and rhodium. And we understood this on the basis of fundamental concepts in metallurgy. When you take an alloy and you oxidize it, you form two oxides, not a single oxide. Iron oxide and rhodium oxide are immiscible. Furthermore, these are cross-sections. You'll see that the iron oxide is preferentially found at the surface, and the rhodium oxide is beneath the surface. And this can also be understood as the basis of metallurgical concepts, because the oxidation of iron takes place by the cations, the iron actually coming out towards the surface. Okay? And in the case of rhodium, there is actually a codiffusion, and the oxygen tends to go in. So because iron is actually coming to the surface, it tends to get pulled to the surface by the oxidation process. Now, if you gently reduce this structure here, this segregated metal oxide structure, 100 degrees C in hydrogen, you'll actually leave a particle which consists of zones of metallic iron and zones of rhodium in the middle state. And the surface will be predominantly iron. And if you look at the chemistry of this surface with its true alloy structure and the chemistry of this surface with its segregated metal form, you'll actually have very different catalytic properties. Next slide. Okay. So just to sort of go over this system in words, immiscible phases of iron oxide and rhodium oxide form during oxidation. Iron oxide is preferentially at the surface because of the mechanism of oxidation. When you go through that low temperature reduction, iron and rhodium are reduced in place. So there's no migration from their relative positions. This results in the formation of reduced iron and reduced rhodium zones with iron preferentially on the surface. When you undergo a high temperature reduction, this is a metastable state incidentally. It's not predicted by the phase diagram. When you go to the high temperature reduction, you get the structure predicted by the phase diagram, which is a true alloy. Next slide. Okay. Now, one of the questions is, of course, well, how can we know this? I don't have time to go over all of the experimental work we've done on this system or similar systems in the last 10 years. I think the most important information, the clearest information, can be found from the calorimetric studies. This is a calorimetric study of oxygen absorption on pure iron on graphite. You see the heats are nice and high, and then they fall off after we've saturated the surface. This is a rhodium catalyst with the same dispersion on the same support. You see the heats are much lower, and the net amount absorbed is also much lower, because iron will actually oxidize down several layers before it passivates. Rhodium, being a no metal, will not. Okay, now let's look at when we have iron and rhodium together on the next slide. All right, this is the iron rhodium catalyst after the low temperature reduction. And you can see that this looks a lot like the pure iron catalyst, which is consistent with what I said the structure is after the oxidation, low temperature reduction, a surface dominated by iron. Now we take exactly the same catalyst, we didn't actually move it anywhere. We oxidize it, reduce it at a high temperature, and we get these triangles. It turns out that the heats here fall immediately between pure rhodium and pure iron, consistent with the formation of a true alloy. The amount absorbed is also far less than the amount absorbed on the low temperature reduced, which is consistent with a noble metal-like alloy surface. It's not going to oxidize multiple layers. So the calorimetry data is one of the many types of data we use to support our conclusions regarding the structure. We also use molecular spectroscopy, X-ray diffraction, a lot of electron microscope work, and we've also shown it's consistent with the kinetics that we've observed, as I'll show you in the following slides. Oh yes, here's pure iron, here's pure rhodium on a normalized curve. Here is the alloy state, or the state after the high temperature reduction. You see it falls midway in terms of heat between the rhodium and the iron. I put this in to remind myself that the iron-rhodium system that's only being used here as an example. Currently, we're finishing some work on iron-palladium. We published some work on iron-iridium, palladium-silver, and this is actually work I did with Andy Chen, now Shell, and Professor Van Ice, with iron-manganese. And in this case, we had a reduced iron-manganese particle. Then we oxidized that particle, and you can sort of see the original particle shape inside, and then all this material that came out. Iron-manganese is a little different. And you can also see that here. Here's the original particle. Here's after oxidation. What was our model of iron-manganese? That was a little bit different. Next slide. So here's iron-manganese. After reduction, the manganese then reduces. It forms a shell. This is the cross-section around iron. During oxidation, consistent with the concepts of metallurgy, you find that the iron diffuses through the manganese oxide shell to form some spinel and also an iron oxide outer layer. And that's what we saw in that last picture. It went from this structure to this structure, leaving a void in the center, which is consistent. Actually, if you take an iron wire and oxidize it, then take a cross-section, you'll find it's hollow in the center. Then if you actually reproduce that structure, you'll find you have metallic iron on the outside, still manganese oxide, and then a void in the center. So it's very interesting structures, but if you apply the concepts of metallurgy, the mechanisms of phase change that are known to metallurgy, two small particles, it all makes sense. And actually, this is taken from a book by Kubachewski and Hopkins, 1967, Oxidation of Metals and Alloys. And you see that they say, well, if you have two metals together and then you oxidize those metals, sometimes one of the metals will become trapped in small particles inside the other. And there's similar diagrams of that nature. And it suggests some of the results that we've been seeing as well. Okay, if we have two different structures, this should allow us to have two different surface chemistries, two different reduced structures, that metastable structure with the predominant iron, and the true stable structure, which is an alloy. Okay. So what we've actually done in the past is we've tested to see if we get different behaviors for two different reactions: butene hydrogenation isomerization, or hydroisomerization, and cinnamaldehyde hydrogenation. And in fact, we found that we had two different chemistries as predicted. For this first reaction, we found that the segregated metal state acted as if it was pure rhodium, even though I said the surface was predominantly iron. Kinetically, in terms of activity and selectivity, it acted like rhodium, if one assumes that 10% of the surface is pure rhodium, because it turns out that iron is completely inactive for this reaction. So even though rhodium is a small component of the surface, it totally dominates the chemistry. And if you look at the turnover frequencies, assuming it's only 10% rhodium, you get good agreement with pure rhodium. In contrast, when you look at the alloy surface of the exact same material in the same reactor, you find that the chemistry is neither that of iron nor rhodium. It actually has the best properties of both. It has the selectivity of iron, which you can find if you go up to about 200 plus degrees C. But it has the activity of rhodium, and rhodium is normally active at room temperature for this reaction. So it's got a nice combination of the properties of both. But it's not exactly like either. So that was, this chemistry was consistent with what we anticipated. And again, we found for cinnamaldehyde hydrogenation, the segregated metal state acted like rhodium because iron by itself is inactive for that reaction, essentially. In contrast, the alloy had selectivity and activity behavior which could not be ascribed to either metal by itself. suggesting that in fact we had some sort of an alloy present. So the catalytic tests were consistent with the model. Okay, here's the butene reaction. Take butene in the presence of hydrogen, and you try to convert one butene to two butene. You need hydrogen, otherwise the reaction is very, very slow because of the mechanism that involves a hydrogen atom. You don't want to get you don't want to get butane. It's an undesired product. Next slide. And here we see the iron rhodium results, as I said, in terms of selectivity. After the high temperature reduction, you see it has very good selectivity. Selectivity is the amount of 2-butene over 2-butene plus butane. And that selectivity is not too different than pure iron. After the low temperature reduction, it's almost exactly the same as rhodium. It has poor selectivity, but good activity. Okay, so here's a second look at that. We have metastable form of a reduced structure. Have the arrow down here. Predominant iron with some rhodium sticking through. Or after high temperature reduction, we get the true alloy. All right, so we wanted to combine some of the ideas from catalysis, going back to the first slide, that have developed basic research over the last few years. The idea that you can actually create a surface in which there are segregated zones, that you don't actually have to make a homogeneous surface. A metal catalyst can actually be multifunctional. We wanted to combine that with the idea of spillover. We also wanted to use a graphite support because that results in the most modest interaction with the metals. So you get sort of the purest metal behavior. And we felt if we knew what we were doing, we could produce a very active, very selective hydroisomerization catalyst for 1-butene. Okay, so here's the mechanism of isomerization. Butene absorbs on, that's what I'm going to try to demonstrate. It's our working hypothesis for some catalysts I'll show in a second. The butene absorbs on the alloy surface. On the same particle, we're going to have some palladium. That palladium part of the particle will dissociate hydrogen. That hydrogen will then spill over onto the alloy surface. Okay. I'll go over this again at the end. That will interact with the butene to form the known intermediate for this process. The intermediate will then lose a different hydrogen atom, and you'll get 2-butene. Okay, let's see the evidence of this model. Here's iron cerium on silicon. Here's our alloy with super selectivity. Now look at that selectivity there. That means this selectivity means in the product mix there is 20 times as much 2-butene as butane. Okay. Sometimes I feel it might be more appropriate to put this in a 2-butene to butane ratio. Okay, so it's 20 to 1, but the temperature is 180 degrees C, very low activity. Next slide. We had a small amount of palladium. All of a sudden we're operating with the same selectivity at 0 degrees C. Okay, it's now 10% palladium or even 5% palladium. We don't see any difference. We have the same selectivity, but now we can operate 180 degrees C lower. So some reason the iron cerium by itself is a rate limiting step. We say that's the unavailability of hydrogen atoms on iron cerium. With the addition of palladium, the reduced hydrogen atoms will spill over. You no longer have that rate limitation. The activity jumps by orders of magnitude. All right, here is pure palladium on graphite. It's a product ratio of 1:1 butane to 2-butene. Here is iron cerium with and without palladium on graphite. It's about 9:1 in the product ratio of 2-butenes to butane. Okay, next slide. Next slide, I have to skip. Next, this is the commercial catalyst, very poor selectivity. Next slide. Next slide. Okay, I just want to show you the model here. A little bit of palladium spills over hydrogen atom onto the iron cerium. It also turns out you can substitute substitute praseodymium or lanthanum for cerium, or cobalt or nickel for iron. There's a whole family of these catalysts. Spills over the hydrogen. That alloy is very selective for the formation of 2-butene, but very inactive. But combining with the palladium's ability to produce the hydrogen atoms, you have very active and very